This is another ranking question, ultimately. We've seen how much I like ranking questions, so it's probably a good idea to ask this. So, first thing to do would be to make sure that you're looking at the proper structure. NO2, COOH, while those work and may be easy to type up, those are pretty useless as far as understanding the overall chemistry of the structure. So what we need to go through and do is, instead of looking at it as NO2, we need to look at the Lewis structure for it. What's the Lewis structure result in?
The ON plus O negative. O double bond.
And the Lewis structure for COOH, I'll zoom back out in a second.
C double bond O with an OH off that.
Okay, and for that last one, stands out. Okay, so what we're trying to do is rank which of these reacts fastest. Okay, what would make something react faster in an EAS reaction? Particularly when we're looking at these rings.
It has more hydrogen or more electrons.
Yeah, in an EAS reaction, our benzene ring acts as the nucleophile. So what we're trying to do is put more electrons into our ring. Okay, so our ring equals nucleophile. It needs to become more negative. Okay, so let's go through and evaluate what things are attached to our ring. So what we're going to do is focus only on what I've been calling atom X, the atom immediately attached to the ring, and try and decide what it has. Okay, so one of the things that you might remember when we started with hydrogen, hydrogen was our 0 point. Okay, so ultimately nothing goes faster, or everything goes faster or slower than hydrogen. Okay, so this is kind of our 0.
Okay, that makes more sense then.
Okay, so then we got to go through and decide on the other two with how they would classify. Okay, and we came up with 2 rules for what atom X could be. Okay, if atom X has more electrons than a hydrogen atom, then it would be an activator. If atom X had less electrons than hydrogen, it's a deactivator. Well, let's take that a step further. What does deactivator mean? Does it react faster or slower?
Slower.
And activator would mean?
Faster.
Okay, so if we go back to our structures and now look at those, in our very first case, what's atom X?
Then nitrogen.
Nitrogen. Does it have more electrons or less electrons than hydrogen?
Less.
It has less by definition because it's positive. Which means if we were going to compare this back to hydrogen, would this react faster or slower?
Slower.
Slower. So to me, that's a bad thing, so I'm going to put a negative next to that. Okay. Because it's reacting slower. We move to the next one. What's atom X?
Carbon.
Carbon. Does that carbon have more electrons or less electrons than hydrogen?
More or less.
Can we draw resonance?
Oh, yeah.
Which atom is more electronegative, carbon or oxygen?
Oxygen.
So we can take these pi electrons and put them up onto that oxygen. What's the result? We lose the pi bond. Our oxygen picks up an extra pair of electrons, becomes negative. What happens to our carbon? It's now formally positive. Okay, which means atom X in this case has less electrons than hydrogen, which means, again,
you didn't actually really need to do the resonance. You know it was partially positive because it's being pulled by the oxygen, right?
Yes.
Okay.
So you could evaluate just based on electronegativity. One of the reasons why I jumped to this is because you can see it a little bit cleaner. Okay. So as far as our rankings go, which of these reacts the fastest?
Hydrogen area.
Okay. Our hydrogen one has to act the fastest. Okay. It may not be, that's supposed to be ist. Okay. It may not be fast, but it's faster than the other two because the other two are deactivated. Okay. So now what we have to decide is which of these is more deactivated. Okay. Which one is taking electrons away more than the other? Okay. Well, what's the charge on our nitrogen?
Positive.
Positive. We could go through and do another resonance structure for that nitrogen as well, just like we did with our carbon. Oxygen is more electronegative than our nitrogen, right? Mm-hmm. So what we can do is take those electrons and we'll put them on that oxygen, which would mean the oxygen would become
Negative.
negative. What would our nitrogen become?
Really positive.
Really bloody positive. Okay, so we still have resonance on this case. So our nitrogen becomes a +2 charge versus the plus it started off with. If we look at our carbonyl, or technically our acid,
It's less positive.
it's less positive, which means
It's faster than the
it should be faster than our nitro. It's less deactivating because it's less positive. Okay? It doesn't need the extra electrons that the ring can supply as badly, and we end up saying that our nitro reacts the slowest, followed by, well, I didn't come up with good descriptions, so I'll just say middle. Okay? So using resonance can really help you out as far as deciding things.
Yeah, that does help.
We didn't have to jump to it. We didn't have to show that that nitrogen was fully that positive. We could just go back and compare. The nitrogen is formally positive. What was the formal charge on our carbon in our best Lewis structure?
Neutral.
Neutral. Positive versus neutral. Which one's more deactivated?
Positive.
The positive. We still come to the same conclusion. Okay. Same idea applies with the rest of those questions. Did I write them? I did. Okay. When we look at the activators, we want to look at their ability to donate electrons. Which atom would be more willing to donate electrons? So let's real quickly change this. Let's say we had, I have no idea if this one's actually in there or not.
Yeah, that one is.
And we'll do CH3. Okay. No foreshadowing here at all as to what the answer might be. If we take a look at atom X, what do we see? In the first case, what is it? Atom X is
Nitrogen.
nitrogen. Okay, does that have more electrons or less electrons than a hydrogen atom?
More.
More, which means
It's an activator.
activator. So if we were going to look at speed, I would give that a positive, because that's going to go faster. If we look at the next one, what's our atom X? Oxygen. Does that have more electrons than hydrogen?
Yes.
Yep, so faster. Last one.
Carbon. Still an
Carbon.
activator.
Still has more electrons than hydrogen. It's a little bit more difficult to see that one, but it does have more electrons. Okay? Because carbon is slightly larger than hydrogen. Okay? So they're all positive, so now which one reacts the fastest? Okay, well, maybe we could come up with which one reacts the slowest first. Which one should react the slowest?
Carbon.
Why would the carbon react the slowest?
Less likely to give electrons.
The electronegative.
Why is it less likely to give electrons?
Because it's the same electronegative.
Because it's fully attached to all the hydrogens.
It's getting more towards it. Does it have any lone pair electrons to
No.
share?
No.
Oxygen and nitrogen both have pairs of electrons that can share, which means if they've got them, they can do it. Carbon can't. It's an indirect sharing. It's known as the inductive effect, which you don't really need to know, but it doesn't share as well. It's going to react the slowest. Okay? So now we move to the other two, our oxygen versus our nitrogen.
So
Take a guess.
nitrogen's slower. because
Why would nitrogen be slower?
it only has one lone pair instead of the two, the oxygen?
Oxygen's got even more electrons than nitrogen, so we might say the oxygen reacts faster. Everybody like that answer?
No, because, well, the
We did.
the oxygen holds on to the electrons. It's not going to actually
it
do
doesn't
it.
share
Oxygen
as
is
well.
more electronegative than the nitrogen, so it
That's right.
holds its electrons. So which answer is correct?
Oxygen's
Oxygen
slower.
is slower.
Nitrogen.
Nitrogen
Faster.
reacts faster. It's more willing to share its electrons. And we would expect it to react faster. If we go back to how many pairs of electrons there are to donate, how many electrons can you donate at any given time?
1, 2,
2 electrons or 1 lone pair. So does it matter that oxygen has more than 1 lone pair? Completely irrelevant. I can only donate 1 at any given moment. So when we do the comparison, it's only 1 for 1. Okay, so we have to come up with something else to explain why. It's not just sheer numbers.
Okay.